Hi everyone, welcome once more to Best Science Brain YouTube channel. So today we are taking a physics content. We're going to take a topic in physics. So this topic is centered on heat energy or thermal energy, and the topic is meant for students in high school, that is senior secondary school, and also for those who are writing external examination like the WAEC examination, NECO examination, and also for students who are in their first year of higher institution. So this topic is also done in first year under thermal physics. So today we're going to cover all the scope we have mentioned, both the students at O level, grassroots level, and also for those in first year or for those who are intending undergraduates. So this topic or this particular lecture session is for you guys. And then we are going to also look at different examples. We're going to take a comprehensive evaluation of this topic. And then under this heat energy, our focus will be on heat capacity and specific heat capacity. We'll not be going to latent heat today. In the next video, we'll look at latent heat. So because of the topic is the topic is voluminous, so we won't break it into two. We're going to do heat capacity and specific capacity, and then the calculations involve explanation in details, taking so many examination questions both for O level, WAEC students, NECO, then JUPEB program, and then those in first year of higher institution. We'll look at the problems involved, and then after this, the next video, we'll now look at the latent heat. So today, our focus will be on heat energy and then the heat capacity and also speaking capacity. So you're welcome once more to the channel. This is your YouTube moderator, Dr. B. And as we go on with this topic, please try to share videos to students in your class or to a WhatsApp group. Introduce students to the YouTube channel. Let them follow us and learn as we teach in this channel. So today we're going to first of all start by defining heat energy. So heat energy, otherwise known as thermal energy, is the form of energy that is transferred between two objects due to temperature difference. Heat energy is the form of energy that is transferred between two objects due to temperature difference. That means heat flows from a hot object to a cold object. So that is, or from a hot region to a cold region. So heat energy, otherwise known as thermal energy, is the form of energy which is transferred between two objects due to temperature difference. Then, having understood what heat is all about, which is a form of energy, sometimes we tend to confuse heat and temperature. So what is temperature? We now say temperature, on the other hand, is the measure of the average kinetic energy of molecules or particles in an object. So we have to know the difference between these two terms, heat and temperature. So we can summarize the difference between heat and temperature using a table or in a tabular form. Let's look at the difference between heat and temperature. So draw a table, heat, and then temperature. So heat energy, we can say this one, it is a measure of the total internal energy of an object. Heat is the measure of the total internal energy of an object, while temperature is the measure of the average kinetic energy of molecules in an object. So the number one difference is based on their definitions. Number two difference, we can say that heat energy, the SI unit or heat, is measured in joules, kilojoules, and of course what we call calories. So we can measure heat in this unit. But out of this unit we mentioned here, the SI unit of heat, SI means standard international unit, is joules. Then for temperature is measured in Kelvin, Celsius, and Fahrenheit. Out of these three units mentioned, the SI unit of temperature or the standard unit of temperature is Kelvin. So these are the major differences between heat, energy, and temperature. One says that heat is the measure of the total internal energy of an object, while temperature will have the measure of the average kinetic energy of molecules in an object. Number two, heat is measured in joules, kilojoules, and calories, where joules is the SI unit of heat energy, or all forms of energy is measured. The SI unit is joules. Temperature is measured in Kelvin, Celsius, or Fahrenheit, where Kelvin remains the SI unit of temperature. So these are the basic differences between heat and temperature. Sometimes in examination, you ask the difference between heat and temperature for those in grassroots or in O level or WAEC, NECO, JAMB programs. So you can have questions on this on the difference between these two items or these two quantities. So having done that, there's a third difference here we're supposed to talk about. A third difference, that's your number three, before I forget, between heat and temperature. Heat is a derived quantity because heat is energy. Energy is derived quantity. Energy is a derived quantity, while temperature is a fundamental quantity. So this is the third difference between heat and temperature. So we're clearing the first two, but this just came to my mind now. So let's go through it again. Then the first one says that heat is a measure of the total internal energy of molecules in a body, while temperature is the measure of the average kinetic energy of molecules in an object. Then heat is measured in joules, kilojoules, or calories, where joules is the SI unit of heat, while temperature is measured in Kelvin, degrees Celsius, or Fahrenheit, where Kelvin is the SI unit of temperature. Then the third one on the board right now is heat is a derived quantity, while temperature is a fundamental quantity. So these are the three basic differences between heat and temperature. So having done that, these two quantities, do they have similarities? Yes. So heat and temperature, do they have any similarity between the two of them? Yes, you should know that both heat, which is energy, and temperature, both of them are scalars. So both are scalar quantities. That is, they have magnitude but no direction. So this is the similarity between heat and temperature. So having done that, we'll now go ahead to what we have today. The major work we have today is we want to introduce what is meant by specific heat capacity. Or before we go into that, we look at the heat content of a body. The quantity of heat in an object. They call it H. So the amount of heat an object is contained in an object. So we can say that the quantity of heat, energy lost or gained by an object. So the quantity of heat inherent in an object depends on three factors. Depends on one, mass of the object. Two, temperature difference, which we can represent using delta, change, T, and then the nature of the body. So the quantity of heat in a body depends, which an object can lose or gain, depends on the mass of the object, the difference in temperature between the initial temperature and the final temperature, and then the nature of the object. So based on what we have itemized on the whiteboard, we can write H very directly as mass and also as change in temperature. What it means is this: the higher the amount of the body, the higher the mass of the body, the higher the amount of heat it will lose or gain. So you can see that. So if you introduce a constant here, we replace the variation sign with equal to. When I say equal to MC, bringing a constant into the formula, into the equation, into this expression. Remove this, bring in the equality sign, and the constant now is your C. So the amount of heat an object loses or gains, given by the formula MC times change in temperature. So that M is mass. Then we have the change in temperature, which is delta theta. With that change in temperature is nothing but the final temperature minus the initial temperature of the object. Then we now have a new quantity called C. So what does that C represent? That C is called the specific heat capacity of the object. The C is called the specific heat capacity of the object. So that's what that C represents. Now, if we make C the subject of the formula here, then bring it up. That equation, H equal to MC times change, make C the subject. C now becomes H all over M times change in temperature. Dividing both sides by M and change in temperature, we'll have this. So, having done that, we now bring the unit. Unit of heat is energy, is joules. There's a unit. Temperature, mass is kilogram. Temperature could be measured in Kelvin or in degrees Celsius. So that will give us joule per kilogram per Kelvin. So this is the SI unit of specific heat capacity. Joule per kilogram per Kelvin. So it's a very important factor in physics or under thermal energy. So now we are going to define this term known as the specific heat capacity of an object. So what do we understand by the term specific heat capacity of an object? So we'll go to the board again, define C. So in physics, the specific heat capacity of an object or a body is defined as the amount or quantity of heat energy required to raise the temperature of a unit mass. The word unit signifies 1. So we want to express this unit in terms of SI. If its unit is 1, we can now say 1 kilogram. But if you want to go with a non-SI unit, you can say 1 gram. So in place of unit mass, someone can say 1 kg of an object through 1 Kelvin. So that is what is meant by the term specific heat capacity. The quantity of heat required to raise the temperature of a unit mass or 1 kg of an object by through 1 Kelvin of an object through 1 Kelvin. So this is very simple to understand. So how do I explain this? Let me just use a particular value to explain this. For instance, in physics, we know that the value of the specific capacity of copper is approximately capacity of copper metal is approximately 400 joule per kilogram per Kelvin. What does it mean, or what does this value imply? It means that 400 joules of energy, 400 joules of energy, cut it here, is required to raise the temperature of the unit here is kg. When I say 1 kg of which substance of copper through 1 Kelvin. You see what it implies? So if we say that the heat capacity of copper is this value, it means you require 400 joules of energy to raise the temperature of 1 kilogram of copper through 1 Kelvin. That's what it implies. Okay? So having done that, take another example. What if you are told that the heat capacity of water is 4.2 joule per gram per Kelvin? You look at the value. This value is not expressed in the unit here is a non-SI unit. Gram is not an SI unit. So what does this mean? It means that 4.2 joules of energy is required to raise the temperature of, I will not say 1 kg here, but the unit here is gram, and I say 1 gram of which substance of water through 1 Kelvin. So I hope it makes sense to you. So that is how the meaning of this was specific heat capacity. Because most examination questions do not intend that you should go and memorize definitions, but try to understand what the definition is talking about. Okay, let's still explain a little more on this term, which is very important term in physics or in thermal energy. For instance, if I have 1 kg of a material, and this material is at initial temperature of, let me say, 40 degrees Celsius. The amount of heat I need to raise this 1 unit mass from 40 to a final of 41, difference is 1, is the specific capacity of that substance. I come again. Let's assume that I have either 1 kg or 1 gram of a substance. That is each is unit of a substance. And that substance is at initial temperature of 40 degrees Celsius. The amount of heat I need to increase its temperature, this 1 gram or 1 kg, from 40 to 41. Difference of 1 is what we call the specific capacity of that substance. So you now understand the meaning of that. Okay, good. So having explained that, we now introduce a new term again, which is different from specific capacity, which is called heat capacity. Heat or thermal capacity, which in physics we can represent using the symbol Cp. Heat or thermal capacity. So what do we understand by heat or thermal capacity? We say this is the quantity of heat energy required to raise the temperature of the entire mass of an object through 1 Kelvin. The amount of heat energy required to raise the temperature of the whole mass. This time around, you're not trying to single out only 1 kg or 1 gram. The whole mass of the object through 1 Kelvin is what's called the heat, or you might say the word heat capacity or thermal capacity. Heat or thermal capacity. The term specific is removed. So we're not specifying the unit mass again. We're not talking about the whole object, the entire mass of the object. For instance, the object may be of mass of maybe 20 kg, for instance. So this is more than the unit mass, or even 20 grams. As long as it's not 1, it's more than the unit mass. So if the initial temperature is perhaps maybe 100 degrees Celsius, the amount of heat required to raise the temperature from 100 to 101, difference of 1, is now called the heat capacity, no longer specific, because the mass you're considering here is the entire mass of the object, a mass greater than 1 unit mass. But if I should bring only 1 kg out of it, out of this 20 gram, only 1 kg, the amount of heat required to raise it from 100 to 101 is now the specific heat capacity. So you see the difference between these two terms in questions. So when you have a question of this nature, you have to be very careful whether the question is talking about specific capacity or talking about heat capacity. So having done that, we now, does this one have any formula or unit? Yes, it has a formula and unit. Remember that heat in a body given by MC, change in temperature. This is mass. This is the specific capacity, the change in temperature. And then from here, the thermal capacity, which is Cp, is given by mass times specific capacity. So the product of mass and specific capacity is given as the thermal capacity of the object. So that means I can modify this formula to be equal to H equal to Cp times change in temperature, replacing Mc with Cp. So you can get your thermal capacity by using, or heat capacity by using mass times specific capacity, or from this formula, you can make the Cp the subject. So here, Cp now becomes H over change in temperature. Now, what is the SI unit of a thermal capacity or heat capacity? Heat is joules, temperature is Kelvin. So the SI unit of this is nothing but joule per Kelvin. So this is the difference. So the SI unit of heat capacity or thermal capacity is joule per Kelvin, but the SI unit of specific capacity, that is this one, is joule per kilogram per Kelvin. See the difference between the two terms. So having done that, we are going to look at elementary problem, a little problem on this, and then we can now go over to other things. So we'll look at a little problem on that for move to other things. So the first question here says, how much heat required at a temperature of 2 kg of iron from 30 degrees Celsius to 70 degrees Celsius? So look at the question. How much heat energy is required to raise the temperature of 2 kilograms of iron from 30 degrees Celsius to 70 degrees Celsius? In bracket, you're given the specific capacity of iron as 460 joule per kilogram per Kelvin. So this question is very simple. Heat energy in an object is obtained using mass times specific times change in temperature. The mass of the iron is given to us as 2 kilograms. Then we have the temperature. We have about two temperatures from 30 to 70. The initial temperature is 30 degrees. The final temperature is 70 degrees Celsius. So difference in temperature will now be the final minus initial, which is 70 minus 30, which is 40. Remember that the difference in Celsius is centered the difference in Kelvin. I come again. The difference in temperature in degrees Celsius is equivalent to the difference in Kelvin. So don't go and start converting this to Kelvin. What am I trying to say? If you convert this one to Kelvin by adding 273, convert this one to Kelvin by adding 273, and then subtract, you must get the same 40. So I did not say that the temperature in Celsius and Kelvin are equal. But what I'm saying that the difference in their values will always be equal. So we're now looking for this. H becomes, our mass is 2. And then before we substitute, we have to look at things. Whether the units are standard. This mass is in kilogram. Then go to the value of the specific capacity is bearing kilograms. So that means there's no unit conversion. Had it been that this is in kilogram and this one is in gram, we may convert the kilogram to gram and before we start solving. But since the units are uniform, we'll now start solving. 2, replacing this, mass is 2, then the value of C is 460. The different temperature is 40. When we solve, we'll have a final answer. And the final answer is 36,800 joules. So we need 36,800 joules to raise the temperature of 2 kg of iron from 30 to 70 degrees Celsius. So that's our first example. So we'll go to example number 2. So number 2 says the heat or thermal capacity of 10 gram of metallic rod. 10 gram of a metallic rod is 42,000 joule per Kelvin. Determine its specific heat capacity. So that's a simple one. That's a simple one. So having done that, how do we solve this problem? So in this problem, we'll look at what's given to us. So we have the mass as 10 gram. And then we have our heat capacity, CP, as 42,000 joule per Kelvin. And we're asked to find the value of the specific heat capacity of the substance. So the first thing we have to do is to convert this. If you look at this, unless we want the value to be in joule per gram, we want to be in standard unit. joule per kilogram. Convert this one to kg. How do you convert? Divide 10 by 1,000. Since 1,000 gram make a kilogram, you have that. So, having done that, so how does, we're looking for the value C, specific capacity. So how does Cp, the heat capacity, relate to the specific heat capacity and mass? We have this formula that says heat capacity given by mass times specific. That's the condition. So make this one the subject. So specific capacity becomes Cp over mass. So having done that, we'll now divide. So that becomes, the value of this is 42,000 divided by the value of mass in kg is 10 over 1,000. You can apply a fraction or knowledge of fraction. That gives us 42,000 times inverting 1,000 over 10 to get our final answer. So we'll solve this. We'll now have 0 cancels 0. So we'll have our final answer as 4200000 joule per kilogram per Kelvin as our final answer. So having done that, we'll now go over to a third question. So the third question says 20,000 joules of heat energy is required to raise the temperature of a substance through 50 degrees Celsius. Calculate the heat or thermal capacity of the substance. So having done that, so this is the quantity of heat required, 20,000. So write our H, heat energy as 20,000 joules. Required to raise the temperature of a substance through, so this heat represents the temperature difference, the change in temperature, 50 degrees Celsius. We're now looking for the value of the heat capacity, Cp. Remember, it's not specific, heat or thermal capacity. So we'll ask ourselves, what formula connects this, and that? Earlier on, we introduced the formula that connects heat and heat capacity, giving us H equal to Cp times change in temperature. Remember that H is MC, change in temperature, and then MC given by is written as Cp. So you make this one, now makes Cp the subject. Cp now becomes H over change in temperature. The value of our heat is 20,000, and the value of our temperature is 50. So you can divide and now have 400 joule per Kelvin, which is, of course, the heat capacity, not specific, joule per Kelvin. That's the right unit. So having done that, so the next session, we're now going to how to determine the specific capacity of substance. The various methods determine the value of the specific capacity of a substance. So how can we determine, experimentally, how can we determine the specific heat capacity of substances in physics? So now we're looking at methods of determining the specific capacity, the specific heat capacity of a substance. And then the substance could be a liquid or a solid. So there are three methods by which we can determine the specific capacity of a substance. And those methods include electrical method, number 2, method of mixture, number 3, mechanical method. For the purpose of this video, we're going to concentrate mainly on the first and second method, which is the electrical method and method of mixture. Mechanical method is mainly for maybe first year students. So there's not much in it anyway. So we're going to look at the first two methods, electrical method and the method of mixture. So we'll go to the electrical method. But first of all, we're going to first of all describe how we can find the capacity of a liquid by electrical method before we now talk about the solid, although there's no much difference between the two processes. So we'll now move to the first one. So with determination of the value of the specific heat capacity of a liquid by electrical method. So in this method, what do we need for this method? So we need, number one, apparatus required. We need one a well-lagged calorimeter. A well-lagged calorimeter. Calorimeter that is a vessel, lag, double wall vessel. Lagging means trying to prevent heat loss using cotton wool or felt materials. Then we also need an immersion heater, or electric heater. We also need a stirrer. We need also a thermometer. We need also a liquid whose mass has determined, or a liquid of known mass. So a liquid whose mass has determined, of known mass. So which is, you can record them, give the mass as M. So that is the equipment required for this experiment. So how do we go about it? So we have a calorimeter, and of course, before we go on, we need a diameter, the voltmeter, the key, and the source of electricity, the Excel. All these are required. So this is a calorimeter, a double-walled vessel, and in between the two vessels, we have the felt, what's called lagging, or cotton wool, to prevent heat loss. Then, having done that, we get a liquid that we want to use, whose mass have determined, is poured into the calorimeter. The mass have already been weighed or pre-weighed for the experiment. Having done that, we now insert our thermometer into this to determine the initial temperature. So we can say let the initial temperature be equal to theta 1 or theta I, the initial temperature of the liquid. After we have done that, we now immerse the heater into it. So the immersion heater is deep inside this. And then connected to the source of electricity. The clean top. Connected our ammeter here in series, and then we have the battery, plus minus, we have our key over there, and then we have our rheostat. The rheostat is adjusted to have a stable current, adjusted until obtain a stable current from the ammeter. You see the way the equipment is arranged. They will have a voltmeter. So that is it. So the process involves that the weight of the calorimeter will be determined, of course. So let me go through it again. I mentioned the equipment required. So we need a liquid. So we can say let the mass of the liquid which we want to determine its speed capacity be M or M1. So let the speed capacity of liquid, the liquid which we are looking for its speed capacity, which is unknown, be C1. Okay? The initial temperature of the liquid. Initial temperature is the temperature you obtained when you did the thermometer inside of it, the thermometer, before you pass current in it, before you connect all this equipment. You have to take the initial temperature of the liquid. Let's call it theta 1. Having done that, then before then, you must have found the weight of the calorimeter. So we can now say let the mass of the calorimeter, the vessel, when it's empty, be equal to M2. So having done that, then now we'll now pass current into this, close the key and adjust the rheostat to stable current value and then pass current into the liquid. So having done that, so let the current passed be equal to I. Let our voltage reading be equal to V, and then we'll pass this current for about 10 to 15 minutes. And then we'll now take the final steady temperature. So when the current has been passed to into this liquid for about 10 to 15 minutes, we'll now have the final temperature of the mixture. Final temperature to be equal to theta 2. So these are the apparatus and then the data we need to determine the speed capacity of a liquid or a non-liquid. So I repeat myself, we have to get a liquid and weigh its mass. The liquid could be it water, be it kerosene, any other liquid, alcohol. We want to find its speed capacity. The mass as N1. And then this is the speed capacity of the liquid you're looking for. Let's call it C1. Then once the liquid is poured into the calorimeter, we'll now take the initial temperature of the liquid. This initial temperature now represents the temperature of the liquid with the calorimeter got that together as theta 1. That they call the initial temperature of the liquid, and also the initial temperature of the calorimeter, because the two of them are in thermal contact. They have the same initial temperature. Then let the calorimeter you're using, let the mass, which are determined for the experiment, be M2. Then you adjust the rheostat until you have a fixed current here. So let the current you're passing be I. Let the potential difference be V. And then the final temperature, which you take after about 10 to 15 minutes of passing current, you now call it theta 2. Having done that, so what assumption do we make in this experiment? You see that the heating coil, which is more like, think of a boiler. When you insert a boiling coil inside water and connect to the circuit, the boiling coil gets hot and then transfers its heat from the filament into the water. So as you see now, the heating coil is the one losing heat, because think of the boiling coil. After you have boiled water for some time, remove the boiling coil from the circuit and put inside cold water to quench the heat. You're going to hear some sound, hissing sound. That means that heat has been transferred from the boiling coil to water. So the heater or the heating filament, this is the heater, electric heater, is the one losing heat. And the heat it loses is then again by the water and the calorimeter. So our principle in this will now be heat lost by heater or heating coil equal to heat gained by liquid in it plus heat gained by calorimeter. You see, so the coil is the heater is losing heat, and the heat is obtained, the electrical energy it gains, it transformed to heat energy in the liquid and in the calorimeter. So whatever energy being conserved, so the heat energy lost by the heater will equal the heat energy gained by the liquid and the calorimeter and its content. So now, instead of saying heat energy, we can still say, so this energy, you can say electrical energy in place of heat energy by the heater of the heater is equal to heat energy gained by liquid and then heat energy gained by calorimeter. So the heater absorbs electrical energy from the electric circuit. And in physics, electrical energy can be given by the formula IVT, current times time times voltage. So the electrical energy lost by the heater is current times voltage times, which is transformed to heat energy given by liquid and calorimeter. So this is the energy lost by the heater. Although this formula can come in different forms. You remember your Ohm's law. Ohm's law tells us that current is voltage over resistance. Now, if I make V the subject, V becomes IR. I can as well make also R the subject and so on. So here, I can make substitution here. So IVT is something as saying, replacing maybe I with V over R. Replace this I, substitute with V over R. I'll have V over R times VT, which is something as V squared T over R. So this formula and these two are the same. So electrical energy IVT is certain as V squared over V squared T over R. So that why I say this can have different variations. Or if I replace, now this time around, replace V with IR. Replace V with IR. I'll have I under I again, IRT. So that will give me I squared R root T. So electrical energy has different format. So electrical energy which the heater loses can be IVT, can be V squared T over R. If you make substitution as I explained, can be I squared RT. So this energy lost by heater again by IVT, V squared over RT, or I squared R root T. They are all equal to each other. So having done that, why the heat energy gained by a liquid is MC, change in temperature. So if you come to this formula, I can now say heat energy lost by heater, which is the form of electrical energy, which can be written as IVT, or any of these, IVT, any of these can be used, equal to the heat gained by liquid, gained by mass of liquid, which we call M1, the capacity of liquid, which is C1, and then the change in temperature. The difference between the final and initial, which is theta 2 minus theta 1. You see that? It's not only the liquid that is gaining heat, also the calorimeter is gaining heat, plus heat gained by calorimeter. The mass of the calorimeter is M2. The capacity of the calorimeter, we can call it C2. And the change in temperature is C, same thing, theta 2 minus theta 1. So with this, we can now look for C1, which is the unknown, or the capacity of the liquid, which we are trying to obtain by experiment. So with this formula, we can solve for C1 when other ones are given to us. But sometimes, the experiment can be performed using a vessel or a calorimeter that has a negligible heat capacity. If the calorimeter has a negligible, means that the heat capacity of the calorimeter is very small, you should ignore it. So if the calorimeter has a negligible heat capacity or heat capacity, that means we ignore the heat gained by the calorimeter. We now use only the electrical energy and equate it to the heat gained by the liquid alone and ignore the heat gained by the calorimeter if it has a negligible or a very small heat capacity. So we ignore this. But whereas the calorimeter doesn't have a small or a negligible heat capacity, it should be included in the calculation. And remember that IVT can be used here, or we can still use this V squared T over R or I squared R root T in place of this. They're all the same thing. Then, mind you, in physics, we talk about power. Power is given by energy expended, E over time. So that means energy is given by power times time. So energy is power times time. And electrical energy in physics is given by IV or I square R or V squared over R. That means if, for instance, as we explained, if energy is IVT and power is energy over time, so divide IVT by time. This cancels. You get IV, which is power. Divide I squared ROT, which is energy, or by time. Since power energy over time, you get I squared R. Divide this one also by time, you get V squared over R. So this is the formula for power. So that means from this equation that says IVT equal to M1 C1 theta 2 minus theta 1, I can replace IV with power. So IV is power, electrical power. Then instead of I write IV, and I write PT, where T stands for power, equal to M1 C1 theta 2 minus theta 1. So if I mean power, so in place of current and voltage, you can use PT, because P stands for current and voltage. So this is something as, from here, energy is power times time. So this energy, of course, is heat energy. So this also represents your heat energy. In place of using IVT, this can also work out for us. So having done that, so you are seeing the different ways by which, or the method by which can determine the speed capacity of a liquid by electrical method, and the calculation involved, or the formula involved in the calculation. The formula is not meant to memorize, but to understand how it's being derived, so you can use it in calculations. Then the next is, how do we determine the speed capacity of a solid by electrical method? In similar way. So capacity of a solid by electrical method, it is similar to that of liquid. What we need a thin vessel, maybe of negligible heat capacity. We need a metal block. A metal block could be aluminum block or copper block. The metal I want to find is heat capacity of mass M, containing 2 holes bored into it. We need also a thermometer. We need also our ammeter, rheostat, voltmeter, key, electric cell or source of electricity, so on and so on. So that are the things we need for this experiment to determine the speed capacity of a solid by electrical method. So having done that, it's a very simple thing. We still get a vessel that has a negligible heat capacity, and then it's lapped with felt or cotton wool. They will place the metal inside of it, a metal whose weight have determined. And this metal has 2 holes, a wider hole bored at the middle and a smaller one bored at the other end of it. So you have 2 holes created deep inside the metal. The middle hole is meant to contain the electrical heater, while the smaller hole is meant to contain the thermometer. So in this smaller hole, we insert the thermometer into it. And to have good thermal contact, you may have some oil, pour some oil, vegetable oil into this before you insert the thermometer, so that the thermometer will have a good contact with the metal. So having done that, let's look at the calculations. So the mass of metal had determined before, after the mass metal determined after the hole has been created. They call it M. Initial temperature of the metal. That is after you put the metal here, you put the metal and take the initial temperature at theta 1 or theta I. Sorry. Then in this hole, we now insert our heater, electrical heater, into this place, and then connect the terminals of the heater to electrical source, our ammeter here, our battery, and then our key, then our rheostat to adjust the current to stable value, and then we'll have this kind of situation. This is our voltmeter. So that is the process. So the key is closed and current is passed into the metal block for about 10 to 15 minutes. We now take our final temperature, theta 2, final state temperature theta F. This is I, or this is F, or let me call this one 1, initial 1 and the final 2. Then current used in the process, they call it I. Potential difference, they call it V. Then time, they call it T for the experiment. So having done that, the concept now we now use here is we now say, see, the same thing, the same concept that applies for a liquid also applies in this situation, whereby the heater is losing heat, the metal is gaining heat. When I say heat lost by metal, by heater, which is electrical energy, equal to heat gained by metal. So the electrical energy which I derived before could be IVT, could be also be I squared ROT, could also be V squared RT, or could also be PT, that is power times time. So this is the heat lost by the metal. So equate any of them to the heat gained by metal, heat lost by the heater, sorry. Then equate any of these. This stands for heat lost by the heater to heat gained by the metal. Metal is M, mass of the metal, which I can call M. Specific capacity of the metal, which I'm looking for, they call it C. The difference in temperature, which would be theta 2 minus theta 1. So from here, you can go ahead and calculate the value of the specific capacity of the metal, which is C, and then get your correct answers. So, having done that, as a precaution, we should know that the calorimeter should be well lagged, or the instrument you're using, the vessel, should be well lagged. And then you take your thermometer readings. Thermometer reading, when it's steady, you ensure that it's steady before you take your final reading. You also avoid error due to errors in reading the thermometer. And then to ensure good thermal contact, the hole in which you place the thermometer should contain some oil. So these are some precautions you take to ensure accuracy in your experiment. So we are now going to quantitative treatment. We're going to calculations involving electrical method. When we are done with these calculations, electrical method, we'll now go to the method of mixture. So we look at this question on the board that says calculate the power rating of an immersion heater used for 10 minutes to increase the temperature of 10 kg of water by 15 Kelvin. In bracket, you have specific heat capacity of water as 4,200 joule per kilogram per Kelvin. So an SSCE equation. I come again. Calculate the power rating of an immersion heater used for 10 minutes to increase the temperature of 10 kg of water by 15 Kelvin. So how do we solve this problem? So let's look at the question. What are we looking for? We're looking for power there. So we're looking for power. Question mark on power. The length of the value is given. Look at the value given to us. So given time, 10 minutes. You have to provide your time in SI unit. 10 minutes is 10 times 60, 600 seconds, convert seconds. The mass of water is already in SI unit, kilogram. Standardize the unit. Very important. Then temperature difference 15 Kelvin. So this determination of heat capacity of water is done by electrical method. So you have power, you have time, electrical power, time, mass, temperature, and then the value of the specific capacity of water. So how do all these values connect? Give a formula which I said IVT equal to MC change in temperature. So this is the heat lost by the heater. This is the heat gained by water, because the heater is the one supplying heat, while the water is the one gaining heat. So, but since we don't have current and time, we're looking for power. I remind you that power is current times voltage. To replace IV with power, PT, equal to MC, change in temperature. So make your P the subject. So P becomes mass times specific times change temperature all over time. So make a substitution. The value of our mass is 10 kg. The value of our C is in bracket 4,200. Then the temperature change is 15. Then our time in SI unit is 600. So you solve this. So 0, 0, 0, 0, 0. So 6 here, 1, 6, 42 is 7. 7 times 10 is 70. 70 times 15 will give us 1050 watts. So that's the power rating of the immersion heater. So you can see the solution. Go to question number 2. The next question on the board says, an immersion heater whose coil has a resistance of 2 ohms is immersed in 4 kg of a liquid. If a current of 10 amperes was passed through the heater for 10 minutes, calculate the rise in temperature. So going to this problem now, what are we looking for? We're looking for the rise in temperature. Define it first. So looking for the change in temperature, delta theta. Then we have the resistance of the heating coil, 2 ohms given to us. Have the mass of the water given to us as 4 kg. Current passed through the coil is 10 amperes. For how long? For 10 minutes. We're now looking for the value of the change in temperature. The same principle applies as in the former question. The heater supplies heat, that loses heat, while the water or the liquid gains heat. So we'll now use IVT equal to MC, change in temperature. So if you use this formula, that may not make you to waste time, because they give us current, they give us time, they did not give us potential difference. Unless you want to go and start finding it, that'd be a waste of time. They give us resistance here. So instead of using V here, we'll now use the other formula which I gave to you as I squared RT. It's equivalent to IVT also. So this one will work out perfectly for you. So having done that, you make D the subject. So the change in temperature becomes I squared RT all over MC, dividing both sides by MC. So having done that, make a substitution. Your I is 10, by 10 square, resistance is 2, and then time is also the same 10 all over. The mass of water is 4 kg, of the liquid, okay, probably water or whatever liquid it is. The liquid capacity of the liquid C is given to in bracket as 4,200. So when you solve everything with your calculator, you're going to get about 7.14 seconds. Sorry, it's in, okay, change temperature 7.14 Kelvin, or you can see say 7.14 degrees Celsius, because the change in temperature in Kelvin and in Celsius remain the same thing. So that is our answer for this question. So in this session, we're looking at how we can determine the specific capacity of a solid by method of mixture. We are done with the electrical method. Now we're going to this other method, which is somehow more complex compared to the electrical method of mixture. So determination of the specific capacity of a solid by method of mixture. How do we do that? So to do this, we need a solid of no mass. So have a solid of mass, let me say M. We need also a calorimeter of mass. Let's call this M2, call this one M1. Okay, let me write it side by side. Calorimeter mass M2. We need water also of mass M3. Having done that, we also need other things like heater, and then thermometer and stirrer. So these are the things we need for this experiment. So I'll briefly describe it and then move to calculations. After the description, it's going to be calculations, all through this topic, or this video, because this is where we have plenty calculations. And these are the actual play that students normally find, normally have issues with. So all we have to do is, we get a solid, we get a beaker, and fill it to half of this volume with water. Then you heat the beaker. As you heat the beaker to high temperature, you now get the solid, which could be a metal like copper, aluminium, tie it to a string and immerse it inside the water that is being heated. Heat it until actually to the boiling point of the water. So when you hit the boiling point of the water, you now put the thermometer here and take the initial temperature. So the initial temperature of the metal which are heating will be very high, something like close to the boiling point of water, 90 degree, 80, or even could be 100 degrees Celsius. So that becomes the initial temperature of the metal, because while the metal is inside the water, the two of them will have the same thermal contact, and they come to what's called thermal equilibrium. Thermal equilibrium is a situation whereby two objects, when they're in contact, assume or come to the same temperature. For instance, when in your room, your body tends to adjust to have the same temperature of your room. So that means you and your room are in thermal equilibrium. So when the metal has been heated to the boiling point, we'll now take the temperature of the boiling water with the thermometer inserted here as the initial temperature of the metal. Having done that, as we're doing this, we have to prepare a well-large calorimeter. Yes, whose mass have determined as M2. That's the calorimeter inside this place. Containing some water. The water here is different from the one that you use for the heating. And the water you place here must use the mass determined also as M3. Then, as you're heating this, you have to also find the initial temperature of this calorimeter and water by placing a thermometer inside of it to find the initial temperature. So the initial temperature of this one, we call it theta2. And this one, the initial temperature of this one is also theta2. Question is this: why do the two of them have the same initial temperature? Because they're in thermal equilibrium together. So when objects are together, they are assumed to have the same initial temperature. So this is kept apart while you heat this. So when this water boils and you take the final temperature of the metal, you quickly, by means of the string, transfer this hot metal into the calorimeter fast without waste of time to prevent heat loss. When you transfer it here, remember that the metal is very hot. So the metal is losing heat, which is given to the water and the calorimeter. So when you transfer the metal, you now stir the mixture to have your final equilibrium temperature. So having done that, we can now have our final temperature, which is steady. We can call it final temperature. We can call it theta3, which is the equilibrium temperature. So having done that, how do we now make our calculations here? So what assumptions do we make here? Before I go ahead for this, I'll still repeat the process or the explanation again. A metal like copper, a piece of copper, aluminum is obtained. Its mass determined, which we call it M1. A calorimeter, empty calorimeter is obtained, lagged, without anything inside of it. Find its mass as M2. Then water, which we want to use for the experiment, the mass was determined as M3. Then after that, the water is poured into the calorimeter. And then we take the initial temperature of the water and the calorimeter. When that together, without the metal in it too. Then the initial temperature of the water and calorimeter will now become theta2. We can call it theta2. These are letters to stand for the initial temperature. Now, the two of them will have the same initial temperature because they are in thermal contact. They come to thermal equilibrium. Now, the metal that you have weighed previously, you now put it inside a beaker of water. This water here is different from the one you're going to use here. So this water inside of it, you don't need to find its mass. Or make sure that you have water that's also half of the volume of the beaker. Then heat the water here, or the metal in it, until boiling point. So when the water is boiling, insert the thermometer inside this place, and then take the temperature of the boiling water, and that is the temperature of the metal in it. Then take the metal by means of a thread, because you cannot hold it when it's very hot, and transfer it quickly into this place, and then stir to get the final temperature of the mixture. So having done that, we now look at the calculations involved. We now ask ourselves, which substance is gaining heat, which one is losing heat? The metal is going to lose heat because it is heated to very high temperature. We now say heat lost by metal. Why this one will gain heat? Heat gained by calorimeter plus heat gained by water. This is water. So in it. So we can now say mass of the metal is M1. Think about the metal which you're looking for. We can call it C1, which is what you're looking for now. The change in temperature now becomes different between the initial and final. So now become theta 1 minus theta 3 equal to heat gained by a calorimeter. The mass of the calorimeter is M2. Think about of the calorimeter, they call it C2. And then the change in temperature will now become theta 3 minus theta 2. Difference between the initial and final. Then for the water, the mass of the water, they call it M3, as you can see that. There. The temperature of water is C3. This actually is C3. The change in temperature of the two of them, because they are together, they will have the same change. Theta 3 minus theta 2. The change in temperature will be the same. Now, if you look at this very well, you see that, look at the change in temperature. If you look at, for the metal, we did initial of the metal minus the final. But for the water and the calorimeter, we did final minus the initial. See the difference? The swerve. Why do we have initial minus final for the metal? Because the metal is at a very high temperature, and you are putting it into something that is cold. So the temperature of the metal will reduce. It's just like when you have this kind of diagram, whereby you have let me just draw a kind of a sketch here. You have a temperature, have a time. The metal is at theta 1. This is where the metal is. Very high temperature. And then the water and the calorimeter is at lower temperature theta 3. This is water and calorimeter. This is our calorimeter Cl. Water and calorimeter. What is our metal M? So you are adding the metal into the water. So the temperature of the metal should go lower. Will fall to the final, which I call theta 2. While this one will rise to theta 2. So you see that the temperature of the metal is higher, will be higher than the final. Okay, I think I call this the final theta 3. I call that of water and calorimeter theta 2. So the temperature of the metal is higher than theta 3. So it's going to be theta 1 minus theta 3, because this one is higher than this. While the water and the calorimeter are gaining heat, these two are gaining heat. So theta 3 will be higher than theta 2. So the change now becomes theta 3 minus theta 2. So I will be very careful of all this kind of information, because in calculations of this nature, if you do theta 3 for metal, if you reverse and say theta 3 minus theta 1, while the metal should have a higher value initial than the final, your answer will give you the solution will give you a negative answer, which is wrong. So for the substance that is losing heat, in heat, thermal energy or capacity, in problems involving heat capacity, for the substance that is losing heat, like the metal, the its initial will always be higher than the final. While for the ones that are getting heat, the initial will be less than the final. So that's what we did. Initial of the metal minus final for the change, and then for the water and calorimeter that is getting heat, final minus the initial for the temperature differences. So please look at that very well and try to understand what we are doing. So having done that, we can now go into some calculations involving heat capacity, those involving 2-component system and those involving 3-component system. So we have the problem on the board that says 250 grams of lead at 170 degrees Celsius is dropped into 100 grams of water at 0 degrees Celsius. If the final temperature is 12 degrees Celsius, calculate the specific heat capacity of lead. In bracket, you have specific heat capacity of water as 4,200 joule per kilogram per Kelvin, and that is a JAM question. So looking at this problem, how do we solve it? We have to list what's given to us. The mass of lead is given to us here. So we can call the mass of lead as M1. So let's write here lead. Mass of lead M1, 250 grams. And if you look at the value, given, or this is expressed in kilogram. This is SI unit, joule per kilo. Why this is in gram. Standardize, convert this to kg, divide by 1,000, that gives us 0.25 kilogram. The initial temperature of the lead is 170 degrees Celsius. Let's call it theta1. It dropped into water. We'll now move to this side. Water, the mass of the water is 100 grams. So M2, 100 grams. Convert to kg, 0.1 divided by 1,000 kg. So the water is at 0. So the initial temperature of the water, they call it theta I, as 0 degrees Celsius. Mind you, the water is not ice block. So we are not talking about latent heat here because they say water as they did not say ice. If I mean the question says ice, will not bring fusion. So it's water. So this substance is water. So no need, is in molten state, not solid. So don't bring fusion here. So the final temperature of the mixture, is 12 degrees Celsius when they are mixed together. We're now looking for the peak capacity of the lead. This is a two-component system. Why does it say two components? We have only lead and water. Yes, of course, water cannot be in air or in somebody's arm. It must be in a container. But the question did not bring the container into the question. That means we should neglect the heat capacity of the container. So we ignore the container and we assume that the container has a very small heat capacity. So we neglect it. So we have only lead and water. So you have a little sketch here. We have the lead at 170 degrees Celsius. This is our lead. We have our water at 0 degrees Celsius. This is water. So you see that the lead is at a higher temperature, losing heat. Water is gaining heat. So when you drop this into the water, the temperature of the water will rise to our final temperature, which is 12 degrees. Here is 12 degrees. So you see that the lead is losing heat, while water is gaining heat. So assumption we make here will now say heat lost by lead equal to heat gained by water. So having done that, you can clean up the question and then solve above. Having done that, we now have the mass of the lead, the heat lost by lead given by MC change in temperature for lead equal to MC change for water. We now equate values. We now input the values. The mass of lead is 0.25. The capacity of the lead is what we're looking for it. The change in temperature. Remember that lead is a higher temperature than the final. The change now becomes 170 minus 12. While for water, the mass of the water is 0.1. The capacity of water given to us in the equation as 4,200. The change is the water is getting heat. So the final is more than the initial. Will now become 12 minus 0. Having solved that, done that, we now have 0.25 times C times, this is 158, equal to, so multiply, this is 420 times 12 minus 0 is 12. We now make C the subject. Solve for C, and that C stands for the peak capacity of the lead. So our C becomes equal to 420 times 12 all over. You solve this out. So 0.25 is 1/4 of 158. But most exams you don't use calculator, so you have to know how to use your brain. 0.25 over 100, which is 1/4. So 4 into 15 is 3. Remember 3. So 4 into 15 is 3. Remember, 3 into 38 is 4 into 38 is 9. Because 4 times 9 is 36. Remember 2, that is 2 over 4. So that at 9.5. So if you solve this value, you get approximately 127.6 as your final answer. Joule per kilogram per Kelvin. So this is the value of the specific heat capacity of lead in the question, and that is the answer to the question. So having done that, we'll go to the next question. Look at that problem, which is an SSCE problem that says, or a problem, question, past question, a piece of copper block of mass 24 grams at 230 degrees Celsius, placed in a copper calorimeter of mass 60 grams, containing 54 grams of water at 31 degrees Celsius. Assuming heat losses are negligible, calculate the final steady temperature of the mixture. In bracket, you have specific capacity of water as 4,200 joule per kilogram per Kelvin, and then you have specific capacity of copper as 400 joule per kilogram per Kelvin. So first of all, we're going to list or itemize what is given to us. We're going to list everything given to us. After listing them, we'll now go to the calculations involved. We can write the question and then solve the problem. So if you look at the question, we have a 3-component system. Why does a 3-component system? We have the copper, the mass is given to you. The calorimeter, the mass given to us. Water, we have the mass given to us. So it's 3-component system. So we want to work with 3 items here. So we have copper listed here. The mass of the copper is given to us in the equation as 24 grams. And since the values of our C's are given in SI unit, convert to kilogram. Divided by 1,000, that gives you 0.024 kilogram. The initial temperature of the copper is 230. So theta I is 230. It's a very high temperature. So it's placed in a copper calorimeter. So the calorimeter is made of copper also. So copper calorimeter. The mass of the calorimeter is given to us 60 grams. Convert also to kg. Divided by 1,000, that gives you 0.06 kg. And then this calorimeter contains water. The mass of the water in it is 54 grams. So 54 grams convert to kg, divided by 1,000, that gives us 0.054 kilograms to standardize the units. Then, had it been that the values of our capacities are given in joule per gram here, we would not convert, we will keep the masses in gram, we won't convert to kg. Okay. Then the water at the temperature of 31. Remember that the water and the calorimeter are together. Since the two are together, they will attain thermal equilibrium and they will have the same initial temperature. As I explained the experiment, when 2 items are together, they will have the same initial temperature. So, assuming heat losses are negligible, calculate the final temperature. We're looking for the final. Can call that theta. So, having done that, so they gave us the heat capacity of water. C of water, they call it CW. 4,200 joule per kilogram per Kelvin. Given to you here. That of the copper, given as 400 joule per kilogram per Kelvin. Then what of the calorimeter? What will be the heat value? The value of that calorimeter, do you expect them to give it to you? It's not given here. But remember that the calorimeter and is made of what? Copper. So since it's made of copper, it will have the same capacity as the copper metal. So it's same 400. So now I have to start looking for it or say that is omission, not omission. When 2 things are made of the same material, they have the same value of speaking capacity. 400, 400, as you can see there. So having done that, we now ask ourselves, which of them is losing heat? Which of them is gaining heat? So if we sketch our diagram, we see copper is losing heat. Why did I say losing heat? Copper is at temperature of 230. So these are copper, a very high temperature. Why 230? Why the water and the calorimeter are at 31 initially? 31 low temperature for water and the copper calorimeter. So this copper was then dropped inside water and calorimeter. So the water and calorimeter will now absorb heat to go higher, will now have a final temperature. So which we are looking for. So you see that the copper has a high temperature, while this one have lower temperature. So the copper will lose heat, while this one will gain heat. So now say heat lost by copper will now be equal to heat gained by water and calorimeter. As simple as that. So we can just have MC change for the copper, MC change for water, plus MC change for calorimeter. As simple as that. So you see that the temperature difference for the copper will now be 230 minus theta, because the copper is losing heat. Final minus initial minus final. While the temperature difference for the water and the calorimeter is going to be theta minus 31, because these two are getting heat. So the theta final will be higher than 31. So you see the difference. These two have the same temperature difference. While this one, look at the temperature difference here. So you have to note all these important points. So we'll move the calculations or to the substitution. Now, having done that, we'll now substitute and then solve gradually. So the mass of copper is 0.024. The mass of copper is 400. Then the heat loss, okay, the change temperature is the higher temperature minus that, as we explained diagram, 230 minus theta equal to, for the calorimeter, the mass is 0.06. Capacity of calorimeter is 400 because it's from the same element of copper. Then the change is getting heat to become theta minus 31. Then plus that of the heat gained by water. The mass of water is 0.054. So capacity of water is 4,200. The change is then theta minus 31. So the two of them have the same change. So when we solve 0.024 times 400, to solve that, we're going to have 9.6. 9.6 into 230 minus theta equal to 0.06 times 400. That gives us 24 into theta minus 31 plus 0.054 times 200 times 4,200. That gives us 226.8. 226.8 into theta minus 31. So open the bracket and then solve accordingly. So that gives us 2208. So if you multiply this, that 2208, multiply that will give you 9.6 theta. Expanding 24 times to give us 24 theta. Then 24 times 31 give us 744. Then plus 226.8 times that give us 226.8 theta minus 226.8 times 31 give us 7030.8. 7030.8. We'll now collect our like terms and solve for theta with the final temperature. So we'll now have a 2208, which is this, plus 744, this one crossing over, the positive sign becomes plus, then plus 7030.8, this one crossing over also becomes plus. So all the terms that are not carrying theta move them to the left hand side, those carrying theta move them to the right hand side, 24 theta, yeah, plus 226.8 theta, then this one going over minus becomes plus 99.6 theta. So we'll add the left hand side. We'll now have a 9982.8. 9982.8. That's what we have after adding all this. Then we'll add the Right hand side we have 260.4 theta. So theta now becomes 9982.8 all over 260.4 to solve for theta, and that gives us 38.4 degrees Celsius as our final temperature of the mixture. So you see how it's done when you have a three-component system. Look at this problem on the board, also involving a three-component system or three items. A metal of mass 0.5 kg is heated to 100 degrees Celsius and then transferred to a well-lagged calorimeter of heat capacity 80 joule per Kelvin containing water of heat capacity 420 joule per Kelvin at 15 degrees Celsius. If the final steady temperature of the mixture is 25 degrees Celsius, find the specific heat capacity of the metal jump. So this is the jump question. So looking at this problem, how do we solve it? We have to identify what is given to us. We have the metal here. We have calorimeter. We also have another item, water. Three items given to us here. So the mass of the metal is 0.5 kg, heated to 100 degrees. The temperature of the metal is 100 degrees Celsius. And then transferred to a well-lagged calorimeter of heat capacity. So what they gave us, a look at the word heat capacity, not specific. There's no specific in it, so you don't make mistake. Heat capacity. So what given to us here is not specific. This is CP. Remember I told you heat capacity is nothing but mass times specific. So it's 80. Look at the unit, joule per Kelvin, not joule per kilogram. So this is heat capacity. So this covers both them. This 80 entails mass times specific. So you don't have to go for mass or specific for the calorimeter again. Then containing water of heat capacity. They also give us the heat capacity of the water as 420 joule per Kelvin. So here, the mass of the water and its heat capacity are included in the 420. And then the water is at 15 degrees. Remember that the water is at 15 and the water is contained in the calorimeter. So since they're in the same container, they're in the same place. So they'll have the same initial temperature because they will achieve or they attain thermal equilibrium. So you can see that. You are now asked to find the final temperature of the mixture. So, okay, we have the final temperature given to us. So the final temperature of the mixture is given to us already. Okay. What are they looking for? We're looking for the heat capacity of the metal, that is C, but the metal is unknown. So we'll take our time to look at the question a little and then we'll now move to solve it. So we'll analyze the question and then pick out the items for the question. We can then clean the question and then start solving this. Then we can still draw our heating curve for explanation or the temperature curve, not actually heating curve. So the metal is at 100 degrees. 100. This is where the metal is. Why the calorimeter and water is at they are 15. This is where you have the calorimeter and water. So metal is dropped into this. Cause the temperature of the water to rise. The final as 25. So you see that the metal is losing heat. The temperature change for the metal will now become 100 minus 25. But the metal has a higher temperature than the final. While for these two, the difference in temperature is going to be 25 minus 15 because the final is higher than their initial. So you have to note all these important points. This and that we're making here. So having done that, so we see that the metal is losing heat. We now say heat lost by metal is equal to heat gained by water and calorimeter. So having done that, you can still say MC change in temperature for the metal. Let M stand for the metal. equal to MC change for the water plus MC change for the calorimeter, cal. I can say, reframe this, MC change for the metal equal to CP times change for the water plus CP times change for the calorimeter. So why did I replace MC by CP in these two cases? Because in the question, what was given to us was the heat capacity of the metal and that of the calorimeter. And the heat capacity entails mass times space. So replace MC by CP for water, MC by CP for calorimeter. It becomes simple for you to solve. So solving this now, we can now make a substitution. So the mass of the metal is 0.5. The heat capacity of metal, we're looking for C, looking for that. The temperature difference is 100 minus 25, which is 75, equal to the heat capacity of the water is 420. The different temperature is 25 minus 15, which is 10, plus the heat capacity of the calorimeter is given to us as 80. The difference in temperature is the same 25 minus 15, which is also the same 10. So solving this out, we'll multiply 0.5 by this, give us 37.5 C. Multiply this, that give us 4,200. Multiply that give us 800. So 37.5 C gives us 5,000. So C becomes 5,000 all over 37.5, and that gives us approximately 133 joule per kilogram per Kelvin, since everything is maintained in SI unit in the equation. So that's the final answer to this question. So we're now going to look at some miscellaneous questions or some simple problems, but tricky, but simple anyway, under method of mixture. So we have one on the board that says two liquids P at a temperature of 20 degrees Celsius and Q at a temperature of 8 degrees Celsius have specific capacities of 1.0 joule per kilogram per degree Celsius and 1.50 joule per kilogram per degree Celsius, respectively. If equal masses of P and Q are mixed in a lagged calorimeter, calculate the equilibrium temperature of the mixture. So you look at this is a two-component system because they only provided the mass of the liquid P and mass of the liquid Q. The calorimeter mass was neglected in the equation. So that means we assume the calorimeter has a negligible heat capacity. So we're dealing with two liquids, P and Q. So, and then from here, there's an assumption we're making here. They say if equal masses of P and Q are mixed together. So that means the mass of P and Q should be the same. So let's take the mass of P as M. The mass of Q remain the same, M. They're not known anyway, but say they're equal. We assume they have the same value. So, and then the initial temperature of our liquid P is 20 degrees. Then the initial of liquid Q is 80, as you can see in the equation, 80 and 20 for P, 20 for Q, 80. And then we're looking for the final temperature, okay? Also, we know they gave us the specific capacity of P as 1.0 in SI unit, and that of our Q as 1.5 in SI unit. So we're looking for, what we're looking for, the final temperature. So we have to sketch a curve here to observe what is happening. So you see that Q is at a higher temperature at 80. So this is our Q. While P is a lower temperature, which is 20. So this is our P. So 20, 80. So the final temperature is unknown, theta. So Q is losing heat. So that becomes the difference, the temperature difference for Q will not going to be 80 minus theta. But this is higher than this. Well, this one is gaining. Difference will be theta minus 20 for liquid P. So having understood that, we can write the equation and then move on to solve the problem. So what we understand here is that Q is losing heat. because it's at a higher temperature, and P is gaining heat. So Q is losing heat. So we say heat lost by Q, because Q is at a higher temperature, 80, and P is getting heat because P is at a lower temperature, which is 20, because the heat gained by P. So MC change for Q, MC change for P. The mass of Q is M. Remember that from assumption, the two of them have the same mass. And the free capacity of Q is 1.5. The difference in temperature is 80 minus theta for Q. Then the mass of P remains the same, M. The free capacity of P is 1. The difference in temperature is now theta minus 20, because it's getting heat. Theta minus 20, as we explained before. M cancels M on both sides. With the bracket, 1.5 times 80, 1.5 times 3 over 2 in fraction times 80. So that gives you 120 minus 1.5 theta. If you open the bracket, this multiply this that, equal to theta minus 20, because this is 1. We'll collect like terms now. To pick your like terms, we now have, we can transfer 120 plus 20 over this side, and then theta plus 1.5 theta. That gives us 140 equal to 2.5 theta. Theta now becomes 140 divided by 2.5. You mustn't solve with calculator, because for the sake of those of you that are writing MCQ or up to test questions, you may not need calculator. So you can use your brain. 140 divided by 2 over 5, 2.5 is 5 over 2. That is 140 times 2 over 5. Inverting, implying mathematics rules for division. So 5, here is giving you 2. Remember, 4 into 40 is 8. Multiply, have 56 degrees Celsius as a final answer. So it's a very simple one. We'll take another one. So we look at this problem on the board that says a tap supplies water at 30 degrees Celsius, while another supplies at 86 degrees Celsius. If a man wishes to bathe with water at 44 degrees Celsius, calculate the ratio of the mass of hot water to that of cold water required. So this is our equation, SSCE. So how do we solve this problem? A tap supplies water at 30 degrees Celsius. So let's assume that this one at 30 should be the cold water. 86 should be the hot water. So the cold water tap, and then hot water tap. So the temperature of the cold water initial is 30, and then the temperature of the hot water initial is 86. And then a man wishes to bath with water at 44. So that means that 44 should present our final temperature. So what are we looking for? We're looking for the ratio of mass of hot water to mass of cold water. So we're looking for MH, where MH stands for the mass of hot water, MC stands for the mass of cold water, which is, or MH over MC. If you're looking for the ratio of mass of cold to hot, should be MC over MH. So you see, for a man to bath or take his bath with water at 44 degree, it means that the man will get some cold water and mix it with some hot water. So this is all about mixture. So if you have to sketch a graph to show what we mean, this is 86 for the hot water. This is 44 for the cold water. And the man wishes to bath with water at what temperature? Okay, the cold water is at 30. The man wishes to bath with water at 44. 44 is the final temperature. So final temperature. So the difference in temperature for the hot water when added to cold water will become 86 86 minus 44. That gives us 42. That is very different for the hot water. And for the cold water that is absorbing heat, the difference is going to be 44 minus 30, which is going to give you 14 degrees Celsius. So the process remains heat lost by the hot water will be equal to the heat gained by the cold water or the colder water. So we'll move to solve this. We can wipe the equation and then we'll make our assumption. Heat lost by hot water, heat gain by cold water, MC change in temperature for the hot water, MC change for the cold water. So the mass of the hot water, we don't know it, we call it mH. Capacity of the water, we call it C. The change in temperature is for the hot water, which is 86 minus 44, that is 42. The mass of the cold water, they call it MC. The capacity of water is C, they call it C. Then the change in temperature is going to be, as we have in the graph, 44 minus 30, that is 14. Have it there. So you see that we can cancel out the C because both are the same substance, as I mentioned earlier on, whether it's hot or cold. As long as it's water, they will have the same value of speed capacity that they will cancel out. So having done that, we're now left with mH times 42, mc times 44. We're looking for the ratio of mass of hot over mass of cold. That's what we're looking for. So divide both sides by mc. We now have mH all over mc times 42 equal to mc times 44 all over mc. So mass of cold water cancels out. We're left with this. Divide both sides again now by 42, so we'll be left with this. Now mH over mc times 42 over 42 equal to, this place is 14, sorry, bring it down, 14, the error, 14 here, equal to 14 all over 42. 42 cancels 42, so the ratio of mass of hot to cold is 14 over 42. We'll have to reduce it to the lowest 10. We'll ask ourselves what we can divide. 7 can divide, let's get it clear. 7 can divide 14, giving us 2. So 7 can divide 14, giving us 2. And 7 can divide 42, giving us 6. We can still break it further. 2 into E7 is 1, into this is 3. So the ratio of the mass of hot water to the mass of cold water will now become 1:3. That's the answer. Not 3:1. 3:1 is cold to hot, but hot to cold is 1:3, as you can see on the whiteboard. So we'll take another example. So let's look at the problem on the board that says equal amount of heat energy supplied to two metals, P and Q. The mass of metal P is half of that of Q, and the specific heat capacity of P is thrice that of Q. Calculate the ratio of the rise in temperature rise in temperature in metal P to Q. Take it once more. Equal amount of heat energy is supplied to two metals P and Q. The mass of metal P is half that of Q, and the specific capacity of P is thrice that of Q. Calculate the ratio of the rise in temperature of metal P to Q. To solve this problem is not difficult. It's a two-component system, P and Q. We have two metals here, P and Q. But the mass of metal P is half of Q. So if I take the mass of metal P as M, then the mass of metal Q will now become 2M, because the mass of metal P is half of Q. So you understand the grammar. Then the mass of metal P is half of Q, and the specific capacity of metal P is thrice that of Q. So capacity of P and Q is bigger. That of metal P is bigger, thrice that of Q. So if I take that of Q, capacity of Q as C, then this one up here becomes 3C. 3 times this, what the mass of this one is 2 times that. We're now asked to calculate the ratio of the rise in temperature of metal P to Q. So we're looking for the different temperatures of P to the ratio of that of Q, or change in temperature of metal P over that of metal Q. So in this problem now, the two metals were not mixed together. We can't mix two metals together in this situation now. But they say equal amount of heat was supplied. So what does it mean? It means that the heat supplied to P is same thing as the heat supplied to Q. So equal amount of heat supplied to the two metals. Does not mean they were mixed together, but since they say equal amount of heat was supplied, so it means that if 1000 joules of heat was supplied to P, it also means that 1000 joules of heat was also supplied to Q. So we apply the same process. MC change in temperature for metal P equal to MC change for metal Q. So if you substitute, the mass of P is M, capacity of P is 3C. For my information here, the change in temperature for P, we'll call it delta theta P. Then the mass of metal Q is 2M. The capacity of metal P is C, and the difference is delta theta Q. So you can see M can cancel M, C can cancel also C. Having done that, we can move up to solve, bring everything up. We now have what remaining here. We have now 3 delta theta P equal to 2 delta theta Q. What are we looking for? We're looking for the change, ratio of the change in temperature of P over that of Q. That's what we're looking for. So to do that, we divide both sides. To get this expression, divide both sides by delta Q. Divide both sides by delta Q, we have the delta theta Q, delta theta Q. So this cancels out. We're now left with 3 delta theta P all over delta theta Q equal to 2. So looking for this expression, so I have to remove 3. Divide both sides by 3. Divide this side by 3. Divide this side by 3. So 3 cancels out. We now have delta theta P all over delta theta Q is equal to what? 2 over 3. So ratio of the rise in temperature of P to the rise in temperature of Q is nothing but 2:3. That is 2 over 3. That's our final answer. So that is it. So we have this question on the board that says an aluminium rod is dropped from a height of 2500 cm. Calculate the change in its temperature. In bracket, we have specific heat capacity of aluminium as 900 joule per kilogram per Kelvin, and the small g as 10 meter per second squared. That small g represents acceleration due to gravity. So look at this. Let's go to the question once more. The aluminium rod, we don't know the mass, so we can say that the mass of aluminium rod be equal to m. The height from which it was dropped is a height of 2500 cm. So since all these values are in standard SI unit, I have to convert this one to SI unit. The SI unit of height or distance is meters divided by 100. That gives you 25 meters. So you're asked to look for the change in temperature of the aluminium as it falls through a height. So how to fully understand this question? The aluminium is falling from a height. Probably, I don't know, could be an upstairs or a hill down to the ground. So we're going to make some assumptions here. So and the height through which it falls is the height of 25 meters. So while the aluminium rod is up there, what energy does it possess? Energy due to height is the potential energy, given by mgh. So energy of an object due to height is potential energy. So this question can also be paraphrased. Instead of using aluminium rod, you can say a waterfall. Waterfall at the top of a dam or in a spring. So So water at a height is also possess the same potential energy. So you apply the same concept. So falls through this height to the ground. So when the aluminium rod strikes the ground, the potential energy is then converted to heat energy, which is MC, change in temperature. Energy being conserved. So if the metal forms, because we know that in the law of energy conservation, energy is changed from one form to the other, but neither destroyed nor created. So when the aluminium rod that possesses energy due to height falls to the ground, it now have heat energy, transformed to heat energy. So what we now do, the assumption here is that potential energy of the aluminium rod due to height is converted to heat energy as it strikes the ground. So we now equate the two energy being equal. We now say potential energy equal to heat energy for the aluminium rod. We now say mgh equal to mc change in temperature. So the aluminium rod, the same mass, you have the same mass because the mass is the property of matter that is constant. The same mass of aluminium up is also the same mass when it falls to the ground. So M cancels M. We're looking for the change in temperature. The change now becomes equal to GH over C. So here G is the acceleration due to gravity given to you. H is the height, 25 meters. And then the peak capacity of aluminium is 900. So when we solve this, we now have 0.28 degrees Celsius or Kelvin as our change in temperature for the aluminium rod as it falls through this height. So we are seeing the basic aspects of heat capacity and speed capacity calculations and the introduction to this topic. Before we go ahead, we have to know that good conductors normally have very low specific capacity. Good conductors have low specific capacity. Like copper is a good conductor, for instance, or silver. So these are very good conductors. So copper, which is one of the good conductors, has a very low speed capacity of 400 joule per kilogram per Kelvin. So this is the specific capacity of copper, very low. Why poor conductors have very high speed capacity, like water. Capacity of water is 4,200 joule. Can you imagine the difference, the wide difference? What it means, it requires a little amount of heat to raise the temperature of copper, unit mass of copper through 1 Kelvin, because it's a good conductor. So you conduct heat fast. But water being a poor conductor, to raise the temperature of a unit mass of water, it requires a high amount of heat. So good conductors have a high specific capacity, while poor conductors have, good conductors have low specific capacity, while poor conductors have high specific heat capacities. Please, that should be noted. And then a good calorimeter that used to determine specific capacity of a substance should have also a low specific capacity and high conductivity. So a good calorimeter and the instrument used to determine heat capacity of a substance should have low specific capacity and high conductivity. So having done that, we are done with the O-level part of this heat capacity and capacity. We're now going to take some questions. We're going to obtain from university book. Therefore, those in first year of the university or those who are doing the JUPEB program in the higher institution. And these questions are exercises obtained from the book Mechanism, Properties of Matter and Thermal Physics. Mechanism, Properties of Matter and Thermal Physics for first year science students and engineering students. So this is the book used by most universities, written by Professor P.N. Okeke and other university lecturers. So we're going to take questions. The exercises we're going to take there are not the ones solved in the book, but the ones given as exercises that are not solved, meant for students to try. We're going to try these questions now. So we'll take the first question from the book, Mechanism, Properties of Matter and Thermal Physics for science and engineering students of first year in the university. We'll have a question there. You see that there's no more difference between this question and the ones we solve for the O-level students. You want to say a container holds 2.4 kg of water at 22 degrees Celsius. Full stop. Into this water is placed a 0.60 kg piece of iron that has a temperature of 95 degrees Celsius. Full stop. Assuming that no heat is lost by the water ion system, what will be the equilibrium temperature of the mixture? So you see that in this question, we are talking about two component system, water and ion. Of course, water is held in a container, but since they did not give us the mass of the container and then did not provide the speed capacity of the container, that means it's assumed that the container has a negligible speed capacity. So the capacity of the container or the heat gained by the container should be ignored. So go to the question. We have water. They are given to us. Water, the mass of water is 2.4 kg. The initial temperature of the water is 22 degrees Celsius. Then inside this water we have an ion placed in it. The mass of the ion is 0.60 kg. And then the East temperature of the ion initial is 95 degrees Celsius. So we're looking for the final temperature. Speaking capacity of the water, given to us at 4,200 in joule in SI unit.